The replacement of the State Route 30 bridge over Bessemer Avenue in East Pittsburgh, completed in May 2016, is a remarkable example of accelerated bridge construction, ABC method. This highly efficient and modern approach allowed a bridge to be demolished and replaced in just 57 hours, a remarkable feat of engineering that minimized disruption to the 22,000 vehicles that travel this stretch of Route 30 daily. The Route 30 bridge that was replaced had originally been built in 1930, over 85 years before it was finally deemed structurally deficient. As a vital artery in Allegheny County, Pennsylvania, the bridge was a critical piece of infrastructure in the region. It connected several communities and served as a major commuter route, making it essential for not only local residents, but also for the transportation of goods and services across the area. The bridge's aging structure presented safety concerns as well as increasing maintenance costs, necessitating its replacement. Given the importance of Route 30, any extended closure of the roadway would have resulted in significant disruption to traffic and the local economy. Therefore, the decision was made to employ accelerated bridge construction methods, ensuring that the new bridge could be installed quickly with minimal inconvenience to the public. Accelerated bridge construction, ABC, is an innovative approach that aims to reduce construction time while ensuring the quality and durability of the final structure. This method often involves the use of precast concrete modules, which are manufactured off-site and then transported to the construction area for assembly. By producing these components in a controlled environment, engineers can ensure higher precision and quality, reducing the likelihood of delays caused by weather or other on-site complications. In the case of the Route 30 bridge, ABC techniques allowed for a bridge replacement process that traditionally could have taken months to be completed in less than 3 days. Around 20 skilled workers were employed on 12-hour shifts to accomplish this, with crews working in coordination to demolish the old bridge and replace it with a new, pre-manufactured structure. The process of replacing the Route 30 bridge was a highly choreographed effort that required careful planning and execution. Once the decision to use ABC techniques had been made, the construction team began by creating precast bridge modules, which included segments of the deck and supporting structures. These modules were manufactured off-site in advance of the scheduled replacement. When the time came for the actual bridge replacement, the old structure was demolished quickly, and its debris was cleared to make way for the new modules. The rapid demolition and assembly process was facilitated by the use of heavy machinery, including cranes that could position the large, precast components with precision. The installation of the new bridge was achieved using a methodical approach that ensured each module was connected and secured efficiently. In total, the entire demolition and installation process was completed in just 57 hours, a significant achievement that stands as a testament to the effectiveness of ABC. One of the key goals of the Route 30 bridge replacement was to minimize disruption to the heavy flow of traffic on this busy stretch of road. Given that Route 30 carries approximately 22,000 vehicles daily, a prolonged closure would have had a significant impact on the surrounding communities and commuters. However, thanks to the careful planning and rapid execution of the replacement, the road was only closed for a short period, and the inconvenience to drivers was kept to a minimum. In preparation for the project, a comprehensive traffic management plan was developed. Detours were established to reroute vehicles away from the construction zone, and clear communication with the public was maintained to ensure that drivers were aware of the changes. This proactive approach helped to prevent major traffic jams and ensured that the bridge replacement caused as little disruption as possible. The North Marmara Highway, a major infrastructure project in Turkey, uses an advanced construction technique called the incremental launching method, or push-launch method. This method is particularly suited for constructing bridges and viaducts over difficult terrain or in areas where traditional construction approaches would be challenging. It provides significant advantages in terms of speed, efficiency, and safety. The incremental launching method involves building the bridge deck or roadway surface in segments at a designated casting area located behind one of the bridge's piers. These segments, made of concrete, are cast sequentially. Once the concrete sets and achieves the necessary strength, each segment is pushed or launched into its final position on the bridge. The process is repeated until the entire deck is assembled across the supporting piers. This technique minimizes the need for temporary scaffolding or supports, making it especially useful when constructing bridges over rivers, valleys, or areas with limited ground access. It also reduces the environmental impact of construction because fewer temporary structures are needed, and the construction process can proceed in a more controlled and safer environment. One of the prominent applications of the incremental launching method in Turkey is on the North Marmara Highway, which includes the third Bosphorus Bridge, Yavuz Sultan Selim Bridge. Frey's Freysinet, a construction firm specializing in such techniques, used this method on several viaducts along the highway, including V17, V6, and V14. These viaducts, integral to the overall highway system, were built using the push-launch method due to the complex geography and engineering requirements of the project. By employing this method, the construction of long spans and large structures is achieved more efficiently and with reduced risks. In addition, the precision of the launching process ensures the alignment of the deck sections, which is crucial for the structural integrity of the bridges. The construction of the cable-stayed bridge to Russky Island over the eastern Bosphorus Strait in Vladivostok stands as a monumental engineering achievement. This bridge, envisioned as a critical infrastructure project, is being developed under a federal program aimed at positioning Vladivostok as a major center for international cooperation in the Asia-Pacific region. Upon completion, the bridge will not only connect the mainland with Russky Island, but will also integrate the island into the broader transportation network of the Primorsky Krai, playing a significant role in the region's economic and logistical development. The bridge, characterized by its impressive dimensions and technical innovations, is one of the most ambitious infrastructure projects in modern Russia. Its height, spanning 70 meters above the water, ensures the unobstructed passage of vessels, essential given Vladivostok's role as the largest Pacific port in Russia. With a central span exceeding 1,100 meters, the bridge sets new world records for cable-stayed spans, while its pylons rise to a towering height of 320 meters. These massive pylons, along with cables extending up to 580 meters, showcase the project's engineering prowess. The construction of this bridge began in September 2008 and was timed to be completed before the Asia-Pacific Economic Cooperation (APEC) summit in 2012, which was to be held in Vladivostok. This tight timeline, requiring completion in just 43 months, was a testament to the scale of the effort and the expertise of the builders involved. Building the bridge across the eastern Bosphorus Strait presented a unique set of challenges due to the region's harsh environmental conditions. The strait, with a width of around 1.5 kilometers in the project area, experiences extreme weather. Wind velocities can reach up to 36 meters per second. Storm waves can rise as high as 6 meters. And in winter, ice formations can be up to 70 centimeters thick. The temperature swings are also significant, from minus 30 degrees Celsius in winter to as high as 37 degrees Celsius in the summer. These factors demanded a design that was resilient to not only natural forces, but also temperature-induced stresses. The choice of a cable-stayed design was driven by the need to minimize the structure's exposure to these elements while providing a sturdy and lasting connection between the mainland and Russky Island. Advanced materials and construction techniques were used to meet these demands. For instance, special concrete mixes that enhance frost and water resistance were employed, with each batch rigorously tested to ensure durability. Additionally, advanced rebar and reinforcement bar testing for tensile strength ensured the bridge's ability to withstand environmental stresses. The bridge construction utilized some of the most cutting-edge equipment and processes available. For example, reverse circulation drilling rigs were used for the first time in Russian bridge construction, along with Bauer BG-40 drilling rigs, the most powerful of their kind in the Far East. Specialized cranes and self-climbing formwork systems were deployed to erect the massive pylons, dramatically speeding up construction time. The logistical aspects of the project were equally impressive. Two main construction facilities were established, one on the Nazim Peninsula and another on Russky Island. These facilities included workshops for welding, building inspection laboratories, and concrete mixing plants. To ensure the timely delivery of building materials, more than 1,300 meters of new railway tracks were built, and an existing 4.5-kilometer railway section was upgraded. Innovative construction techniques were also employed, particularly in underwater construction. The pile footing for the pylons was built from the water using temporary steel caissons, with drilling and concreting operations conducted offshore, a first for Russian bridge building. The 120 board piles supporting each pylon were as much as 77 meters deep, showcasing the technical difficulty and complexity of the foundation work. The bridge's pylons, crucial to the structure's stability, were designed with a varying cross-section, tapering upwards to better distribute the immense loads they bear. The lower sections, which carry the most stress, were reinforced with high-grade concrete to ensure maximum durability. Self-compacting concrete, a material that flows into place without the need for vibration, was used to improve the quality and speed of construction. The pylons were built in 4.5-meter-high sections using custom-made self-climbing formwork, which reduced construction time by nearly half. The aerodynamic profile of the central span was tested in a wind tunnel to ensure it could withstand the region's frequent high winds. The span itself is made of steel box girders, with panels pre-assembled at nearby production facilities before being transported by barge and lifted into place. The stiffening girder, composed of 103 panels, stretches 1,244 meters and weighs 23,000 tons, making it one of the largest and most complex components of the bridge. The N40 South Ring Road flyover scheme at the Sarsfield roundabout in Cork represents a significant infrastructural development aimed at improving traffic flow in one of the city's busiest areas. Central to the success of this project was the use of large-scale cranes, including CHL 350-ton and 500-ton capacity cranes, which played a crucial role in the installation of critical components like bridge beams and other heavy materials. The Sarsfield roundabout, a major junction on the N40, experienced heavy congestion before the upgrade, particularly during peak hours. The flyovers were designed to alleviate this by allowing free-flowing traffic on the N40 while reducing bottlenecks at the roundabout itself. The project involved the construction of overpasses and the installation of large precast concrete beams, which required precision lifting and placement due to their significant weight and size. The CHL 350-ton and 500-ton cranes were instrumental in this phase of the construction. These cranes, known for their heavy lifting capabilities, were deployed to lift and position the concrete beams onto the support structures. The use of such high-capacity cranes was necessary given the substantial weight of the precast beams, which can weigh several tons each. The 500-ton crane, being the larger of the two, was used for the heaviest lifts, ensuring the beams were safely and securely placed without risk to workers or the structure itself. Precision and safety were key concerns during the lifting operations. The cranes were operated by highly skilled professionals who carefully coordinated each lift with the construction crew on the ground. Given the proximity of the site to active roadways and the ongoing flow of traffic, safety protocols were strictly enforced. This included conducting lifts during off-peak hours to minimize the impact on traffic and reduce the risk of accidents. The CHL cranes, with their advanced lifting technology and robust design allowed for efficient and safe placement of the beams, which in turn expedited the construction schedule. Their use on-site helped minimize delays, ensuring the project could proceed smoothly without compromising on the structural integrity of the flyovers. In addition to their lifting capabilities, these cranes were chosen for their versatility and mobility. They could be quickly moved into position and set up, reducing the time required for each operation. This efficiency was critical in keeping the project on track, particularly given the tight deadlines and the importance of minimizing disruption to Cork's busy road network. The construction of a steel structure factory building involves a series of methodical steps, each crucial to ensuring a strong, durable, and functional structure. The process begins with detailed design and planning, where architects and engineers create comprehensive blueprints and structural calculations. At the site, the steel structure is assembled. This involves erecting the main framework by positioning and securing steel columns and beams using cranes and other heavy machinery. Bolting and welding are used to connect the components firmly. After the main structure is assembled, secondary elements like flooring, roofing, and wall panels are installed. The building undergoes thorough inspections to ensure it meets all safety and quality standards. The construction process concludes with a final inspection to verify compliance with all specifications. Once approved, the building is handed over to the client, ready for operational use. This systematic approach ensures a robust and efficient steel structure factory building. Polypond pond lining is an essential innovation in water conservation, especially beneficial for farmers and the aquaculture industry. Water seepage is a significant problem in tanks, ponds, and canals, leading to substantial water loss and reduced efficiency. Polypond addresses this issue by providing a durable, impermeable lining that retains water effectively. For farmers, especially during droughts, a pond liner is invaluable. It allows for the storage of water, making it available for agricultural use independent of monsoon rains. This ensures a reliable water supply for crops, enhancing agricultural productivity and sustainability. In the aquaculture industry, polypond linings are crucial for preventing saline water from contaminating adjacent fields. This helps in maintaining the quality of both the aquaculture environment and neighboring agricultural lands. Polypond is one of the most affordable and effective geomembrane liners available. Manufactured to international quality standards, it offers superior puncture and tear resistance compared to other geomembranes. This is achieved through the use of high-quality materials, virgin resins for consistency, LDPE coating for UV stability and welding properties, and a high thread count HDPE scrim for enhanced puncture and tear resistance. To protect the pond liners from sharp objects, layers of sand, concrete, or fiber matting can be used. The liners are manufactured in rolls, and strips can be seamed or welded together on site. Flexible liners can also be prefabricated to fit specific pond designs, with edges secured either in a trench or to a vertical wall. The Tunker's 60.2 HVB vibratory hammer is a powerful hydraulic machine designed for efficient pile driving in marine construction. It delivers high-frequency vibrations to drive steel piles into solid substrates quickly and effectively, ensuring stability and precision. The soil test evaluates the substrate's stability for driving 40-foot, 30-inch diameter piles, ensuring the ground can support the pile's load and confirming the construction site's suitability. Template installation involves setting up a guide frame to ensure precise alignment and positioning of piles during marine construction. This framework secures the piles at accurate intervals and angles, facilitating efficient driving and enhancing structural integrity by maintaining uniformity throughout the piling process. Marine pile driving is a critical process in marine construction involving the installation of long, slender columns or piles into the seabed to support structures like piers, docks, and offshore platforms. This technique is essential for ensuring the stability and durability of marine infrastructure. The process begins with a thorough site assessment, including soil testing, to determine the seabed's composition and load-bearing capacity. A template or guide frame is often installed to ensure the precise positioning of each pile. Specialized equipment, such as vibratory hammers or hydraulic impact hammers, is used to drive the piles deep into the substrate. Vibratory hammers apply rapid vibrations to reduce soil resistance, allowing the pile to penetrate smoothly. Hydraulic impact hammers deliver powerful blows to drive the pile to the desired depth. Mechanical concrete is an innovative road construction technology developed by American civil engineer Samuel Bonasso. This method, introduced in 2017, has been recognized by the American Society of Civil Engineers as the most environmentally friendly construction method due to its unique approach to utilizing recycled materials. The core of mechanical concrete technology lies in the use of discarded tires, which are a significant environmental issue globally. Every year, major cities accumulate vast quantities of used tires, creating disposal challenges and environmental hazards. Bonasso's solution repurposes these waste tires into a valuable construction resource. In mechanical concrete, the circular shapes of old tires are filled with gravel, creating a strong, stable, and flexible foundation for roads. This technique not only addresses the critical problem of tire waste, but also enhances road durability and reduces construction costs. The gravel-filled tires form a cellular confinement system that improves load distribution and prevents soil erosion, making the roads more resilient and longer lasting. This method significantly cuts down on the need for traditional road construction materials and processes, which are often resource-intensive and environmentally damaging. By integrating tire recycling into road construction, mechanical concrete presents a sustainable and effective solution to modern infrastructure challenges. The MBW MK8-75 Lowrider is a versatile ride-on trowel designed for both floating and finishing applications. With over 25 years in production, LOWRIDERS have been instrumental in the development of riding trowels. This extensive experience has led to the creation of a high-performance, low-maintenance line of ride-on trowels. Lowriders feature a simple design with fewer moving parts, a highly reliable drivetrain, and the use of top-quality materials. These machines set industry standards for performance, durability, and ease of maintenance. The MK8-75 is the smallest ride-on trowel in the industry, weighing 460 pounds. It is ideal for both large and small jobs, multi-story flooring, and areas where larger machines cannot operate effectively. This trowel is compact enough to be transported in a pickup truck, pass through a 32-inch doorway, and function as an edging trowel. It excels in both floating and finishing tasks. Engine: Honda GX 390 blades, 8 troweling path, 63 inches, 161 centimeters, 100 inches, 254 centimeters, 76 inches, 194 centimeters. Fuel: gasoline rotors, 2 rotor speeds, up to 130 RPM, up to 125 RPM, up to 180 RPM. Plastering machines represent an innovative approach to applying common gypsum plaster, offering an efficient and smart solution for construction and renovation projects. These machines streamline the plastering process, significantly reducing the manual labor traditionally required and enhancing productivity and consistency in application. The basic operation of a plastering machine involves mixing the plaster material to the right consistency, which is then fed into the machine. The machine sprays the plaster onto walls and ceilings with precision, ensuring a smooth and even coat. This method not only saves time, but also minimizes material wastage, leading to cost savings. However, it's important to note that using a plastering machine is not as straightforward as it may appear. Proper trials and examinations of the methodology must be conducted before executing any plastering work. Trained operators and applicators are crucial for the successful operation of plastering machines. Skilled personnel can handle the equipment efficiently, adjust the settings as needed, and ensure a high-quality finish. FP McCann's precast tank system offers an efficient and reliable solution for water storage, waste management, and various other applications. The installation process of these tanks is designed to ensure durability, safety, and quick assembly, making it a popular choice for both commercial and residential projects. The installation begins with a thorough site assessment to determine the most suitable tank type and size based on the specific needs and soil conditions. Once the site is prepared, a precise excavation is carried out to create a level and stable base, ensuring the tank will be properly supported. Next, the precast tank sections, which are manufactured under controlled conditions to meet high-quality standards, are delivered to the site. These sections are typically designed to be easily handled and transported, minimizing logistical challenges. Using cranes and other lifting equipment, the sections are carefully lowered into the excavation site. The modular design of FP McCann's tanks allows for quick and secure assembly, with sections being seamlessly joined using specialized seals and connectors to ensure watertight joints. After the tank is assembled, it is backfilled with appropriate materials, often a mixture of gravel and soil, to provide additional support and stability. The installation process also includes connecting the tank to necessary plumbing and drainage systems, ensuring it integrates seamlessly with existing infrastructure. Installation with positional couplers is an efficient method used in construction, particularly evident in projects like the Granta Park Cambridge BAMTech installation. This process begins with laying track spacers under the B1 layer in the conventional manner. The B1 layer is then rolled out straight over columns where positional couplers have been precast. Upon completing the B1 layer, the B2 layer is rolled out at a 90-degree angle to the B1 layer, ensuring structural integrity and load distribution. The central collar of the positional coupler is then placed onto the bottom male half, which is already cast into the column. Following this, cranked bars, equipped with the second male half of the positional coupler, are installed, ensuring a secure connection. The installation continues with the placement of prefabricated perimeter U-bar details between the bottom and top mats, further reinforcing the structure. Heavy-duty wire high chairs are positioned to support the top carpet mats. These top carpet mats are then installed with cranked terminating column bars situated between the bottom and top mats, completing the installation process. The use of positional couplers significantly maximizes productivity. Fabricating larger BAMTEC roll mats or carpets increases production output by covering more area per installation session. The installation of Kobiax modules involves accurately positioning them on the slab as per the design layout. Modules are spaced uniformly to create the necessary voids within the concrete, reducing weight without compromising strength. Proper alignment is critical to ensure structural integrity. They are then secured in place, ready for the initial concrete pour. Concreting the first layer involves carefully pouring concrete over the Kobiax modules, ensuring they are completely covered and securely embedded. This initial layer stabilizes the modules, preventing any movement during subsequent construction phases. Concrete is evenly spread and compacted to fill any gaps around the modules, ensuring a uniform surface. Proper curing and monitoring are essential during this stage to achieve the desired strength and prevent any settling or misalignment before proceeding to the next layer. Concreting the second layer involves pouring concrete over the entire slab, encompassing both the cobiax areas and the surrounding sections. This layer is spread evenly and compacted to ensure a uniform and level surface. Adequate curing time is observed to achieve optimal strength and stability, finalizing the slab with a robust and integrated structure. Step 1. Column installation. Column installation is the foundational step in the steel erecting process for the side plate field bolted connection. This stage begins with the delivery of prefabricated steel columns to the construction site. Each column is precisely measured and inspected to ensure it meets the project specifications. The columns are then positioned on the prepared foundation, which includes base plates with pre-drilled holes for anchor bolts. Using cranes and lifting equipment, columns are hoisted and placed vertically, ensuring they are plumb and aligned with the building's layout plan. Anchor bolts are inserted through the base plates into the foundation, and nuts are tightened to secure the columns in place. The use of leveling instruments, such as transits or laser levels, is crucial to verify that columns are perfectly vertical and correctly spaced. Once the columns are anchored and verified for accuracy, temporary bracing may be used to maintain stability until the beams are installed. This precision in column installation lays the groundwork for the entire structural framework, ensuring subsequent construction stages align seamlessly. Step 2. Beam installation. Beam installation follows column setup, where steel beams are lifted and positioned between the columns using cranes. The beams are temporarily secured and aligned with precision to ensure levelness and correct placement. Workers use alignment tools and measuring devices to verify proper positioning. Temporary bolts or clamps may be used to hold the beams in place. Proper alignment is critical to distribute structural loads effectively and prepare for the secure field bolted connections in the next step. Step 3. Bolt installation. In this step, high-strength bolts are inserted into the pre-drilled holes of the side plate connections, fastening beams to columns. Bolts are tightened to specified torque levels, ensuring a secure and durable connection that meets engineering standards. Step 4. Gap closure and fireproofing by general contractor. In the final step, the general contractor addresses any gaps between connections to ensure airtight and watertight seals, enhancing structural integrity and protection. Sealants or fillers are applied to close these gaps effectively. Following this, fireproofing measures are implemented to protect the steel structure from high temperatures in the event of a fire. Fireproofing materials, such as intumescent coatings or fireproof boards, are applied to the steel components. Building and maintaining America's roadways is essential but also hazardous, claiming the lives of over 100 workers annually. To address this, Pioneer Industrial Systems has developed the Robotic Maintenance Vehicle, RMV, a groundbreaking solution to perform road maintenance tasks, specifically crack sealing, without exposing workers to the dangers of traffic. The 480-volt three-phase state-line generator provides reliable, continuous power to the RMV's systems, ensuring consistent operation without interruption. Sealmaster Crack Pro. The Sealmaster Crack Pro sealing unit is a top-tier crack sealer designed for durability and efficiency. The integrated air blow-off system clears debris from cracks before sealing, enhancing adhesion and effectiveness. The advanced AI vision system combines high-resolution cameras and lasers to detect and measure cracks accurately. The RMV setup is straightforward. The robot auto-positions for heating, the truck is lowered, and the operator safely configures the equipment from the cab for seamless operation.